This video will only cover the introductory basics of covalent bonds and will not discuss the existence of sigma or pi bonds. I have a full video on this and a further video on naming covalent compounds on my channel. Let's begin. Covalent bonds are the most common types of bonds, and this is due to the fact that the possibilities for their existence are very broad. A covalent bond is when two atoms share valence electrons with one another, oftentimes to complete their full valence electron octet. It's important to note that, unlike ionic bonds, covalent bonds are not a full transference of electrons. Rather, they are the sharing of valence electrons between atoms. This sharing is what is known as covalent bonding, literally covalence bonding. Covalent bonds are generally between two nonmetals, shown on this cutout of the periodic table. This is because, while nonmetals have the electronegativity to attract electrons, their difference in electronegativity is not large enough to fully form an ionic bond. To fully understand this, let's take a look at this periodic table showing the electronegativity of each element. If sodium, an element with an electronegativity just under 1, was to form a bond with chlorine, an element with an electronegativity of just over 3, the electronegativity of the chlorine atom could easily pull sodium's valence electron and form a full ionic bond. However, if we were now to form a bond between an oxygen atom with an electronegativity of 3.44 and a carbon atom with an electronegativity of 2.55, the difference in electronegativity between the two atoms would not be great enough to form a full ionic bond. Therefore, a covalent bond would form. It's also important to note that two metals would not form a covalent bond. Rather, they would form a metallic bond, which has very different properties. Now that we've talked about the properties and grounds for existence of covalent bonds, let's look at some examples. A famous example of a covalent bond, and one that you will certainly be familiar with, is the one existing between the oxygen and hydrogen atoms in water. Let's take a closer look at how this covalent bond can form. So we have here a fully drawn out oxygen atom and hydrogen atom. Apologies for my lopsided circles. Remember also that oxygen has an electronegativity of 3.44 and hydrogen has an electronegativity of 2.2. Remember that electronegativity is just the tendency of an atom to attract electrons towards itself. This oxygen atom has 6 valence electrons and wants a full octet containing 8. This hydrogen offers 1 valence electron. Remember that if atoms collide with the correct orientation and sufficient energy, a bond can form. Because the oxygen atom is more electronegative than the hydrogen, it will pull this hydrogen's electron towards itself. So let's now imagine that this oxygen and this hydrogen atom will collide with sufficient energy and orientation. This is how the oxygen and the hydrogen atom would now appear. Notice how this electron is being shared by both the oxygen and the hydrogen atom. Remember that because oxygen has the greater electronegativity than hydrogen, although the electron is being shared by the oxygen and hydrogen atom, the oxygen atom is actually pulling on the electron more. It has more ownership over the electron. Because oxygen has the partial negative charge, we assign it a lowercase delta negative. Because hydrogen has the partial positive charge, we assign it a lowercase delta positive. Again, to repeat, electrons are negative. And so because the oxygen has a higher electronegativity, it will pull more of the electron towards itself. Because it is pulling more of the electron compared to the hydrogen, which is pulling less, the oxygen will have more negative and the hydrogen will be more positive. Lastly, because the oxygen is partially negative and the hydrogen is partially positive, we call this bond a polar covalent bond. That is when we have the unequal sharing of electrons in a covalent bond. I will show this process again, this time with the molecule hydrogen fluoride. So, again, here we have a fluorine atom and a hydrogen atom. This fluorine has 7 valence electrons and thus wants to complete its octet by acquiring 1 more. This hydrogen atom has one valence electron. If the fluorine atom and the hydrogen atom collide with sufficient energy, they will be able to form a bond. Fluorine is the most electronegative element, having an electronegativity of 3.98, and hydrogen's is 2.2. Because of this, although this electron is shared between the two atoms, the fluorine atom will possess more control over the electron. It will pull it closer to itself than the hydrogen atom will. So again, this is a polar covalent bond. Assigning partial charges to each element, we see that because the fluorine has more control over an electron, which is negative, the fluorine will be a partial negative charge. So we assign it the lowercase delta negative. And because the hydrogen has less control over a negative electron, it will be positive. So we assign it a lowercase delta positive. Let's do this one last time using the molecule fluorine gas. Both of these fluorine atoms have a very high electronegativity, 3.98 each. If these two fluorine molecules, upon collision with one another, have sufficient energy, they will form a covalent bond. This covalent bond has these two electrons being covalently shared between the two fluorine atoms. Again, similar to the bond in hydrogen fluoride and in the water molecule, these electrons are being shared between each fluorine atom. However, notice that each fluorine has the same electronegativity. Because of this, this is a non-polar covalent bond. The electrons are being held equidistant from each fluorine atom, so there are no partial charges to assign. Nonpolar covalent bonds, such as this one found in fluorine gas, will exist amongst atoms with the same electronegativity or a symmetric atomic structure. To finally finish off this video, I'd like to reiterate some of the points with some drawings that might make more sense. Let's imagine that this molecule here on the right is hydrogen fluoride, this being the fluorine atom and this being the hydrogen atom. We can see that the bigger fluorine atom is bigger because it has more electrons than the smaller hydrogen atom, which has less electrons. Again, this is why the fluorine will have the partial negative charge and the hydrogen will have the partial positive charge. Thank you for watching this video on covalent bonds, and I hope you have walked away with a better understanding of their properties, how they are formed, and their different classifications.